How can feedback control systems compensate for delays and latency? Imagine trying to keep a ball balanced on a moving platform while the signals to move the platform arrive late. That's similar to what feedback control systems face with delays and latency. When signals take time to travel or process, the system can become unstable or sluggish. But engineers have clever ways to fix this. They use predictive control, which involves creating a model of how the system behaves. This model helps the controller guess what will happen next based on current and past data. So, even if there's a delay, the controller can act as if it has real-time information. Another method is adjusting the feedback gain dynamically. Instead of using a fixed setting, the controller changes how strongly it responds depending on how long the delay is. If the delay gets longer, the controller can reduce its response to avoid overcorrecting or causing instability. Some systems include special delay compensators. These are like smart filters that analyze the current delay and adjust control signals accordingly. For example, in networked control systems, the controller might send a sequence of commands, and the compensator picks the best one once the delay is known. Event-triggered control is also useful. Instead of constantly sending signals, the system only updates when something important happens, like a big change in the system state. This reduces the amount of data sent and helps manage delays better. State estimation techniques are another key tool. They use algorithms called observers to reconstruct the current state of the system from delayed or missing measurements. This way, the controller can still make good decisions even if the data arrives late. Some control systems relying on models to predict how delays will affect the system and then adjust their actions accordingly. Others use adaptive control, which learns and changes its parameters over time to handle unpredictable delays. Combining these strategies helps keep the system stable and responsive, even when delays or latency are present. In real-world applications like robotics, power inverters, or network control systems, engineers often combine predictive control, delay compensation, and state estimation. This mix ensures the system stays stable and performs well despite the inherent delays. For example, in a robotic arm controlled over a network, these techniques help the robot move smoothly without jerks or instability caused by communication delays. So, in essence, feedback control systems use a variety of smart strategies to predict, adjust, and estimate, making sure they work reliably even when signals are late or delayed. This keeps everything running smoothly, no matter what kind of latency challenges come their way.